pleasant day to everyone po. So we are the Group 5 from DSTE 31 and today we're going to be presenting our discussion about fluid flow in pipes. So specifically, we're going to cover in this lesson, of course, the description, critical velocity, friction and velocity distribution in pipe, head loss in pipe flow, pipe friction, coefficient of pipe friction, frictional loss in laminar flow, pipe friction coefficient, wetted perimeter, hydraulic and energy gradients, other pipe formulas, Manning and Hazen-Williams diagrams, minor losses. And aside from that, we're also going to discuss the branching pipes, the trigger circle. So without further ado, let us start now. So let's start with the most basic question. So ano po ba ang pipe? No? So obviously speaking, alam naman natin na ang pipe is just a closed conduit na nagtatransport ng either liquid or ng gas, no? That is under pressure. Na gusto ko lang i-emphasize po yung under pressure kasi hindi lahat ng makikita nating tubo is considered as a pipe, no? So for example, yung tubig na nanggagaling from our water source, di ba? They are transported under pressure, so therefore they are called pipe, no? Unlike for example, yung sewer line natin, hindi naman sila nangangailangan ng pressure, no? Kapag itatransport nila yung fluid doon. So therefore, it's not considered as pipe, no? But rather an open channel instead. So yun yung parang distinction. Pipes dapat, they should be under pressure, yung fluid na dinadala niya. So the next thing is, ang pipe, hindi lang siya gawa sa plastic, no? Na usual na nakikita natin. But it can also be made of steel, fiberglass, no? And concrete. Okay, that carries slurries and fine particles. And as I've said, ito yung nakita natin sa houses, no? Yung from our water source, and mostly sa mga industrial, like sa chemical process plants. No? So ganito po yung itsura niya from the left side picture. No? Ito yung parang itsura ng pipe na nagtatransport ng tubig to our houses. At sa right picture naman, yung pipes na nagagaling sa industrial processes na usually ay puro gas ang laman. So next thing is, ever wondered bakit ba circular in shape ang pipes natin? So ito, sabi rito, most pipes are in circular form because it offers the least resistance to surface friction. So ano ba yung surface friction na yan? Ganito kasi yan. Di ba, ang fluid natin kapag nag-flow siya sa pipe, nagkakaroon or nagde-develop ng friction. Ngayon, pag meron ka kasing nade-develop ng friction, nagkakaroon din na tawag natin head loss or energy loss, which is to be discussed later on. So that's why kailangan natin i-take into consideration yung surface friction. No? It should be of least resistance. Now, the thing is, ang circle kasi, compared sa other polygons, say for example, square, no? Meron silang mas maliit na perimeter compared sa other polygons nga. At dahil may maliit sila na perimeter, of course, meron silang maliit na surface area. At dahil maliit ang surface area nila, therefore, it will offer the least resistance, no? Sa shape na circle. That's why they are circular in form, no? Commonly. Okay? So, additionally, sabi po na it has low initial cost and it provides the highest rate of flow. And there is minimum deformation that is seen kapag meron kang external pressure na applied. Okay? So, let's go to critical velocity. So, critical velocity is just simply the velocity na kung saan nagbabago ang fluid mo from having a laminar flow to turbulent flow. So laminar flow and turbulent flow, na-discuss na to sa previous discussions. And we know that laminar flow, ito yung characterized by having a low velocity movements. So syempre, kung meron siyang low velocity movements, yung individual particles sa fluid na yon is may sinusundan na tinatawag nating well-defined path. No? Kumbaga hindi sila gulo-gulo. Para silang straight line, nag-form ng straight line, or not necessarily sobrang straight, but rather, alam natin na may defined na path, no? Unlike sa turbulent flow naman na kabaliktaran ng laminar flow, this is characterized by having a high velocity movement. At dahil mabilis ang movement, yung individual particles niya is nagkakagulo-gulo, kaya they keep on crossing within each other. So hindi na nila nasusunod yung tinatawag na well-defined path. Okay? So next, critical velocity experiment. So this is Osborne Reynolds, by the way. Wait lang. Ayan. So, this is Osborne-Reynolds, by the way. So, noong 1883 po kasi, nagkaroon tayo ng experiment. Or rather, si Osborne-Reynolds ng experiment. Where this is your glass tank. This glass tank is filled with water. This is your glass tube that has its bulb at one end at meron namang bell mouth sa other end po. Now, this is your injector, a color, that contains colored dye. No? So, sa simple experiment niya, ang ginawa niya lang po is that yung valve daw, nung binuksan niya ng dahan-dahan yung valve, now logically speaking, kapag binuksan natin ang valve ng dahan-dahan na, of course, magkakaroon from having zero velocity to a low movement na velocity, no, mabagal lang. So, nung ganun lang niya binuksan yung valve at nag-inject siya ng colored dye, ang nangyari daw po is that yung colored dye is hindi nag-mix dun sa water. Means, may sinusundan siya sa sariling path niya at yun niya, hindi siya humahalo. Whereas nung tinodo naman ni Osborne ang pagbukas ng sa valve na yon, and again, logically speaking, pag tinodo mo ang pagbukas ng isang valve, bibilis ang movement ng fluid. So therefore, magugulo yung individual particles ng dye. At ganun nga ang nangyari, naggulo na, hindi na nasunod yung ang nangyari ay nagmix na siya doon sa water. Okay? So ganun lang po yung naging experiment ni Osborne-Reynolds. So to have a further, or to further understand rather this concept na an experiment, nag-provide po ako ng links para ma-visit mo. Okay? So additionally daw, dun sa experiment po ni Reynolds, nalaman daw po natin yung tinatawag na transition point from turbulent to laminar flow. No? So according to him, sabi niya, it would require a smaller velocity kung gusto mong baguhin ang fluid na may turbulent flow patungong laminar flow compared sa laminar flow to turbulent naman daw. And this is what we call the upper and lower critical velocities. So para mas maintindihan natin yon kung ano yung upper and lower critical velocities, let's take a look at this figure. Okay. Now, this is the flow condition. Flow condition sa isang pipe having a 1/2 inch in diameter. Okay. So this is a time versus velocity that is in feet per second graph. No? So this is your line OA. No? At kung makikita nyo, meron siyang streamline flow or the laminar flow. Well, this is your line AB at meron siyang turbulent flow. So let's start first with the line OA. So sa line OA, having streamline flow, initially, ang sabi po ron, kapag hindi na-disturb yung tubig sa part na to at hindi siya tumaas ng velocity up to 3 point something feet per second, ang flow niya is mananatiling streamline flow lang or laminar flow. Pero kapag yung velocity niya is tumaas sa 3 point something feet per second, dun na magsisimulang mag-emerge si turbulent flow. Kung baga, mag-iiba na siya from streamline flow to turbulent flow. Okay? Next naman, sa line AB na may turbulent flow initially, sabi naman po, kapag hindi nag-decrease yung velocity niya for up to, let's say this is 0.5 feet per second, ang flow niya is mananatiling turbulent. Okay? Pero kapag bumaba na sa 0.5 feet per second ang velocity niya, ang mangyayari, mag-iiba siya from turbulent flow to streamline flow or laminar flow condition na. Okay? So ito yung tinatawag natin na higher critical velocity and lower critical velocity na tinutukoy ni Osborne-Reynolds. Okay? So to conclude, alam natin na meron laging certain velocity which is the lower critical velocity na kung saan lagi mag-e-exist si laminar flow. Ganun din kay upper critical velocity na lagi mag-e-exist turbulent. So sa pagitan ni upper and lower critical velocities, sa part na to, dito sa pagitan na yan, there will always exist either streamline flow or turbulent flow depende sa kung ano yung naging initial condition niya. Dahil kung streamline flow ba siya nung una or turbulent flow ba siya nung una. Okay? So another thing is, sa experiment niya, si Osborne-Reynolds is nakapag-develop din po siya ng criterion para malaman ang flow ng isang fluid. And that is what we call the Reynolds number. So Reynolds number is simply a dimensionless parameter para malaman nga natin yung flow rate ng isang fluid. So it has this formula that is equivalent to VD rho over mu or VD over small letter v. Okay? Where V, of course, is the mean velocity in meters per second, diameter of the pipe, that is in meters. Rho is your density in kilogram per cubic meter. Mu is your dynamic viscosity in Pascal. seconds. Okay? And then itong small letter v is the ratio of the dynamic viscosity to the density, which is also what we call the kinematic viscosity. This is the formula of your Reynolds number para ma-determine natin ang flow type ng isang fluid. According kay Osborne, sabi po rito, it was observed to be that 2,000 is the upper limit for laminar flow, 3,000 is the lower limit for turbulent flow, and the value between them, which is called the transition region, can either be laminar or turbulent. So anong ibig sabihin nun? Sabi niya, kapag meron kang value ng Reynolds number na, let's say, 2,000 or less than 2,000, it means that yung flow type ng fluid mo would be laminar. Whereas kapag meron ka namang value ng Reynolds number na 3,000 or higher than 3,000, it means that the flow type is turbulent flow. Okay? At kapag nakakuha ka ng Reynolds number na sa pagitan ng 2,000 at 3,000, that is what we call the transition region. Na again, sabi ko kanina, it can either be laminar or turbulent depende sa kung ano yung initial condition niya. Okay? Next po is let's try to solve this problem. Now, calculate the Reynolds number of the fluid having a viscosity of 0.6 Newton second per square meter and a relative density of 850 kilograms per cubic meter flow through a pipe with a diameter of 25 millimeters and a velocity of 2.5 meters per second. So apply given si data, no? 2.5, 25, 850, 0.6, and then apply lang natin yung formula ng Reynolds number, VD rho over mu. So that is equivalent to 2.5 times 0.025 times 850 over 0.6. And the answer is 88.542. So based sa criterion again ni Osborne Reynolds, hindi naman siya lumagpas sa 2,000. So therefore, this flow of fluid is considered to be laminar. Okay? Next po. Now, what is the profile of velocity of fluid in the pipe? No? So ano ba itsura ng velocity kapag nasa loob siya ng pipe? Yung fluid, velocity ng fluid. So this is the cross-section of your pipe. No? Kung mapapansin nyo, parabolic ang shape ng velocity profile ng fluid. Kasi are with the maximum velocity occurring at the center. Now, ito yung sinasabi ko kanina sa friction thing. Now, kung mapapansin nyo, yung maximum velocity is mag-occur siya sa middle kasi siya yung farthest dun sa pipe wall. Again, kapag sa pipe wall at sa fluid may contact, nagkakaroon ng friction. At pag may friction, of course, magkakaroon ng head loss, magkakaroon ng decrease in the velocity. Kaya kung mapapansin nyo, as you approach patungo dun sa pipe wall, bumababa yung value ng velocity. Okay? Kaya nagmumukha siyang parabolic. Okay? Now, of course, if yung pipe mo is frictionless, and obviously speaking, magiging straight lang to. Magiging same lang yung velocity distribution niya. Mapagitna, mapadulo, no? If frictionless. If not, magiging parabolic siya. Now, if the pipe is bent, no? Ngayon, if balik mo naman yung pipe mo, ang mangyayari naman dyan, from being the center having the maximum velocity, ang mangyayari, mag-move yung maximum velocity sa part na form yung concave. So dito, na-bend siya pa-concave, therefore umangat yung maximum velocity mo. At same thing pa rin, if presence si friction sa pipe walls, of course, mariretard yung fluid, ang mangyayari, mababawasan yung velocity hanggang sa papalapit siya ng papalapit dun sa wall ng pipe. Okay? Next is the velocity distribution. Now, we have this term pipe factor, which is simply the ratio of the V over Vmax, where your V is the mean velocity sa pipe, no? And your Vmax is the maximum velocity in your pipe that is occurring at the center. Okay? Now, Karman and Prandtl presented that the velocity distribution in the mainstream is represented by the relation. Na ito yung relation mo. V is equivalent to Vmax times Y over R raised to N. Where N is obviously a constant, and it is equivalent to 1 over 7 if you have the Reynolds of about 100,000. 1 over 8 naman siya if you have your Reynolds number between 100,000 and 400,000, but for smooth pipes. No? If rough pipes naman, then the value of N would be 1 feet. Okay? Now, itong small letter V na to, that is the velocity of the fluid particle that is at y distance from the wall of the pipe, having radius r. Okay? Vmax, again, is the maximum velocity occurring at the center. Okay? Now, this is what we call the relation na pinresent ni Karman and Prandtl. Okay? Now, next thing is the graph of the pipe factor as a function of Reynolds number. Ibig sabihin, pwede mo rin daw pala mahanap si pipe factor when you have the Reynolds number, no? Now, this is the graph of it, no? So, let's try this example. No, for a given Reynolds number of 100,000, calculate the radius of a pipe with y that is equivalent to 15 millimeters from the pipe wall. Now, since given naman si Reynolds number na 100,000, of course, ma-determine na natin si value of the constant and 1 over 7. And by plotting from the table, so, di ba, dahil given si Reynolds number 100,000, makahanap din natin yung value ni pipe factor, which is approximately, dito siya, so this is, let's say, 0.82. Okay? So, meron na tayong value ng pipe factor. So again, this is the equation. So divide lang natin sila both sides by Vmax para makancel si Vmax dito at makuha mo si pipe factor dito. Okay? So 0.82 equal to 15 over r raised to 1 over 7, and solving for r, we determine 60.17 millimeters. Okay? Next po. Now, head losses in pipe flow. Okay. So what are the head losses in pipe flow? Ito yung binabanggit ko kanina na energy loss, no? So ayan, also known as the energy loss, and is measured in joules per Newton or simply in meters kasi ang joule natin is equivalent to 1 Newton meter. Therefore, canceling your newtons. Ang matitira ay yung meter. Okay? So ngayon, yung head losses daw po sa pipe, pwede sila makategorize as major or minor loss, no? With major being the pipe friction. The reason kung bakit siya ay major kasi ang pipe friction is ito yung most common na nag-occur sa isang pipe, no? Ito yung kadalasang nangyayari na loss. That's why classify siya as major loss. And that is further discussed later on, no? Ang minor losses naman, ito naman yung mga local disturbances na natawag natin or what we know as the form losses naman, no? So, next, puntahan natin yung local disturbances na yan. No? So, sa local disturbances na yan, or form losses, meron tayong 4 na head losses, na dahilan ng head losses. No? So, una, is we have the head loss due to the sudden contraction of the pipe's cross-section. This is denoted by H sub C. Siyempre, kung merong contraction, meron kang enlargement, and this is denoted by H sub E. Thus, next is due to obstruction caused by the gate valve, denoted as H sub O, and meron ka ring head loss due to pipe bend that is denoted by H sub B. Okay? So, dun muna tayo sa sudden contraction. So, di ba dahil meron kang sudden contraction or biglang lumiit yung cross-section ng pipe or even gradual contraction, ang mangyayari, of course, obviously speaking, mag-increase yung flow velocity ng fluid. Ayun, yung biglang pag-increase ng velocity ng fluid na yun yung magkakos ng minor loss, no? So, imagine niyo, di ba, dati, kapag gumagamit tayo ng hose, tapos kapag gusto natin pabilisin yung velocity niya, ang ginagawa natin is tinatakpan natin ang daliri natin ng bahagya, yung butas niya, no? And that is equivalent to having sudden contraction sa pipe, kaya bumibilis yung velocity niya. So, parang ganun yung analogy niya. Okay? So, ganito yung itsura niya. Sa left picture, makikita nyo yung pipe na nagkaroon ng sudden contraction. So, we know that sa part na to, yung velocity dito sa part na to will always be less than kaysa sa velocity sa part na to kasi nag-contract na siya. Or sa right picture naman, this is a venturimeter by the way, na ginagamit pang measure ng flow rate ng fluid. Dito naman sa part na to, alam natin na ang velocity dito sa upstream part na to will always be less than sa velocity dito sa throat kasi nag-pass through siya sa converging cone na gradually ay lumiliit. Okay? So, next is the head loss due to sudden enlargement naman. So, again, kung meron kang contraction, meron din sudden enlargement. So, syempre, kapag bigla naman lumaki yung cross-section ng pipe mo, of course, obviously speaking, babagal yung velocity ng fluid mo. At yung kapag bagal ng velocity na yan, yun yung nagkakos na tinatawag natin minor loss. Okay? So, at the scenario ng hose, ngayon, di ba nakatakip yung daliri mo? Kapag biglang inalis yung daliri mo, di ba that is equivalent to having sudden enlargement sa cross-section. So, ang nangyayari, bumabagal ulit yung tubig o bumabalik siya sa original na niya. Okay? Now, ito yung itsura niya. So, sa left Sa left side ng picture, ito yung itsura ng pipe na nagkaroon ng sudden enlargement. And we know here that the velocity in this part will always be faster than the velocity in this part kasi dito ay nag-decrease na siya dahil sa sudden enlargement. Or again, dito sa Venturi meter naman, alam natin na ang velocity dito sa throat part will always be faster than the velocity at the downstream part. Kasi pass through siya sa diverging cone na gradually ay lumalaki. Okay? So, ayan po. Next is the head loss due to obstruction. Ayan. So, sabi rito, the closing of valves causes in the decrease of flow section. So, therefore, this creates the minor loss. No? So, para mas magets nyo, ganito ang itsura ng gates or valves natin. No? So, dito muna tayo sa part na naka-close siya. Kapag naka-close siya, alam naman natin na wala kang movement dyan. There is zero velocity. Now, if dahan-dahan mo bubuksan yan, of course, dahan-dahan na magkakaroon ng velocity. From having zero velocity to reaching its maximum velocity. So ngayon, kung ganong change na yon is yung nagka-create ng minor loss, no? Yung pagkakaroon ng biglaang velocity or increase in the velocity. Same case dito naman kapag naka-open yung valve mo. Di ba kapag naka-open siya at dahan-dahan mong sinara, of course yung velocity niya is magiging from having maximum velocity papunta sa zero velocity kasi magsasara siya. So ngayon, yung change in velocity na yun, yun yung nagkakos ng tinatawag natin na minor loss. Okay? So next po is head loss due to pipe bend. So ito yung binanggit ko kanina na kapag may irregularities sa pipe, no? Or bend siya. Obviously speaking, di ba, ang flow direction ng fluid is sinusundan niya lang naman yung sa container. So, yung ganon, yung change in the flow direction, yun yung nagkakos na tinatawag natin na minor loss. Okay? So, simply ganito ang itsura niya. So, sa part na to, nagkaroon siya ng bent or change in the flow direction. Therefore, pag nag-pass through yung fluid sa part na to, magkakaroon ng tinatawag natin minor loss. Okay? So, yun yung apat na head loss, no, or yung local disturbances. So, to conclude, we know that the summation of the head losses in pipe flow is equivalent to H sub F. Ito yung tinatawag nating major loss or yung pipe friction to be discussed later, plus the H sub C, plus H sub E, plus H sub O, plus H sub B. Na ito yung apat na diniscuss ko po kanina. So, that's it po. Thank you.
So, pipe friction. So, in head losses due to pipe friction, the head loss is primarily linked to the friction, which in turn depends on the properties of fluid, as well as other parameters like velocity, diameter of pipe, and internal roughness of pipe. So, friction losses occur as fluid passes through pipe fittings, bends, and pressure drop due to change in elevation of fluid. So, while calculating for head loss, one must account for a total of energy losses due to the length of pipe and those due to fittings, valves, and other system structures. So for velocity distribution under laminar flow conditions, so meaning the flow is smooth and even, the resistance to flow is affected by the viscous shear between particles which move in parallel paths but under different velocities. So particles in contact with the pipe walls do not have any motion. So this particular condition is called the no-slip condition. So velocity is zero at the pipe wall. But the other particles sliding over then experience viscous shear which decreases to a minimum value at the center of the pipe. It is the shearing stress or viscous shear between moving fluid layers that determines how the velocity varies across the pipe section. So velocity distribution under turbulent flow conditions is dependent not only on viscous shear, known by its misnomer of pipe friction. So friction losses in pipe are termed as major losses, while loss of energy due to change of velocity of flowing fluid in magnitude or direction is termed as minor loss. So major energy losses are usually calculated by Darcy-Weisbach formula. So as we have seen, friction losses are the primary source of head loss. Friction losses closely depend upon the type of fluid flow. So by finding out the Reynolds number, we can find out whether the flow is laminar or turbulent. For laminar flows, fluid friction is proportional to velocity of flow and is independent of pressure, proportional to contact surface area, and independent of nature of surface. So for turbulent flow, the fluid friction is proportional to velocity of flow, is dependent of pressure, and proportional to contact surface area, meaning the longer the pipe, more will be the loss. And density of flowing fluid depends on nature of the surface. So in here, in the pipe wall, so this is where the no slip condition occurs, and the velocity here is 0. And the maximum velocity is usually at the center of the pipe. So this is applicable only for the laminar flow conditions. Darcy-Weisbach equation. So this equation was developed by Henry Darcy and Julius Weisbach. So Darcy equation, so the equation is flashed in the PPT presentation. So head loss is denoted by H sub F. So F is the coefficient of pipe friction, L is the length of the pipe, D is the internal diameter, V is the mean velocity, and G is the gravitational pull. So coefficient of pipe friction, or F, for straight smooth pipes which carry water under turbulent conditions, fanning gives the average values of the pipe friction coefficient F for different pipe diameters and mean velocities of flow. So in this table, in some problems, the diameter of the pipe and the velocity are given. So when those two are given, so you can find the coefficient of pipe friction by referring to the table. So for the sample problem, a city water supply pipeline consists of a new 60 centimeter cast iron pipe. Compute the frictional loss of head per kilometer of pipe when the discharge is 0.35 cubic meter per second. So in here, the diameter is given, so 60 centimeter, so that's 0.6 meters. And the other given information is 0.35 cubic meter per second. So that is the discharge. So we can use that to calculate the velocity. So 0.35, the discharge over pipe, all over pipe pi over 4 multiplied by the d, the diameter 0.6 squared. So with that, we will get a velocity of 1.24 meter per second. So we have the diameter and we also have the velocity, meaning we can find the coefficient of pipe friction. So by plotting from Fanning's table, F is determined to be 0.018. So let's go back to the table. The diameter of pipe is 60, so it's somewhere around here. And the velocity is 1.24 meter per second. So it's somewhere around here. So we can see that the coefficient of pipe friction is 0.018. So we have all the needed information. We will input all the values to the formula of the head loss. So coefficient of pipe friction is 0.018. The diameter is 0.6. The mean velocity is 1.24 and gravitational pull 9.81. So with that, we will come up with an answer of 2.35 joule per Newton. So that is the head loss. So for sample problem number 4, determine the discharge of water through a 90 centimeter wood stub pipe if the loss of head is 5 joule per Newton in a length of 1,600 centimeter. So we are finding here the discharge of water. So that is Q. And the diameter is given as well as the head loss or loss of head and the length of pipe. So by using the given information, we can find the discharge first by using the previous formula, which is volume is equal to Q over pi over 4 diameter squared. So the diameter is given. Then this volume, we will substitute it to the formula of head loss. So head loss is equal to coefficient of pipe friction multiplied by L over D times V squared over 2 times G. So the V here, we will substitute it with this formula. And by manipulating the equation, we can put all the variables together and leave the Q or the discharge at the other side of the equation. So we will yield with this equation. So inputting the given values, so 5, that's the head loss, given head loss, 5 joule per newton. The diameter is 90 centimeter, 0.90 meter. Length of pipe is 1,600, and the coefficient of friction 0.016, which is coming from the Fanning-Stein wall. So F ranges from 0.015 to 0.018 for pipes with the diameter of 90 centimeters. So going back, so the pipe is around 90 centimeters. So here we can see that 0.015 to 0.018, that's the range of the coefficient of pipe friction. So we will assume that the coefficient of pipe friction is 0.016, and with that, we can find the discharge. So after calculating this given equation, we come up with an answer of 1.18 cubic meter per second. So for sample problem number 5, what diameter of wood stave pipe should be installed to carry 1.42 cubic meter per second of water for 8 kilometer with a loss of head of 1.5 joule per newton? So we are finding for the diameter, and the given values are the discharge, the length of pipe, and the head loss. So for this problem, no reference diameter or velocity is available to find F. So we assume any practical value. So any, for example, 0.020. So by using the formula, volume is equal to Q over A. So A is pi over 4 multiplied by D squared. And that formula from the volume, we will insert it to the formula of the head loss. So there's the value of volume in the head loss. So it's the same procedure as the previous problem. So putting the diameter, isolating the diameter on the other side of the equation, we can find the diameter, so 0.083. Then the coefficient of friction that we assumed is 0.20. So the length of pipe is 8 kilometers, so 8,000. 1.42, so that's the Q from the equation, that's the discharge. And the head loss is 1.5 joule per newton. So the diameter is 1.78 meters. So again, if we use the formula V is equal to Q over A and insert the value of diameter that we have come up, it's 0.57 meter per second. So that's the volume, the velocity, I mean. So we have the value of the velocity and the diameter. We can refer to the Fanning table. So we should, with the diameter of 1.78 and velocity of 0.57, the coefficient of pipe friction should be 0.020. So let's check. So the diameter is 1.78 meters. So that's around here, 178. And the velocity is 0.57. So velocity is 0.57, so it's around here. So we can see that the coefficient of friction is 0.012. So the assumed value, the initially assumed value was 0.020. So we can say that this is a wrong assumption. So in this problem, we can see that the coefficient of pipe friction is crucial for the Darcy-Weisbach equation. So again, let's try another value. We will try 0.13. Then using the same procedure, we will come up with a diameter of 1.63 meters and a velocity of 0.68. So let's check that in the table. So the diameter is 1.63 meters, so that's around 163, somewhere around here. And the velocity is 0.68, so it's somewhere around here. 0.13, 0.013. So that's the same value that we assumed. So from that, we can see that it's okay. So we were finding the diameter. So the diameter, the answer for this problem is 1.63 meters. So next, sample problem number 6. Water pumped through a vertical 5 centimeter new galvanized iron pipe to an elevated tank on the roof of a building. The pressure on the discharge side of the pump is 1,380 kilopascals. What pressure can be expected at point in the pipe 76 meters above the pump when the flow is 9.5 liters? So for this problem, the diameter is given, so 5 centimeter, and the velocity is unknown. So again, using the equation that discharge over area is the velocity, we can find that the velocity is 4.84 meters per second. So we have the diameter and velocity. Again, we will refer to the Fanning table. So 5 centimeter and 4.84. So the diameter is 5 centimeter and velocity is 4.84, somewhere around here. The coefficient of pipe friction is 0.0223. So we have the coefficient of pipe friction. We can solve for the head loss. So inputting all the given values, we have the head loss of 41.7 joule per Newton. So in this scenario, we can apply the concept behind the Bernoulli's equation. So we will use this formula for points 1 and 2. And since V sub 1 is equal to V sub 2, we can simplify the formula from this to this. Then, calculating this equation, we come up with the answer, the pressure is 225 kilopascals. So that is the pressure at the point here, 76 meters above the pump. So the answer in this problem is 225 kilopascals.
Okay, now let's go to Hagen-Poiseuille equation. So, first of all, an interesting fact about this equation is noong 1839, na-derive ito ni Hagen, and on 1840 naman, ang nakaderive naman itong equation na ito ay si Poiseuille. So, masasabi natin na this equation was experimentally verified independently but almost simultaneously ng dalawang different investigators. So, sa slide na to makikita natin na ang equation, ito ang equation ng Hagen-Poiseuille at ito naman ang equation ng coefficient of pipe friction. So next slide. In this figure, makikita natin ang isang stirred pipe na nag-flow under steady laminar conditions. And makikita natin na meron siyang L, which is yung horizontal length, pressure P1 and P2, which are the average pressures. And throughout the length of the pipe, meron tayong makikitang concentric cylindrical shell na tatawagin natin ABCD. Ito ay merong radius na Y and thickness na Ty. Mula lamang sa figure na ito, madederive natin ang Hagen-Poiseuille equation. Paano nga ba natin siya madederive? So mag-start tayo sa equation na almost every one of us know, which is F is equal to PA or force is equal to pressure times area. From this figure, delta F is equal to pressure P1 minus P2 times yung area niya pi y squared. Okay. Alam din natin na ang head loss is equal to pressure drop P1 minus P2 all over specific gravity or W. So masasabi natin na P1 minus P2 is equal to W times HF or specific gravity times head loss. Okay. So substituting this to the previous equation, we now have delta F is equal to WHF times pi y squared. Okay. So ito ay masasabi natin na matatawag natin itong incremental force na nag-act sa ating cylindrical shell ABCD. Incremental force. So nasabi kanina na ang ating pipe ay under steady laminar conditions. Ibig sabihin, nasa equilibrium siya. Meaning, merong force na nagka-counteract dito sa ating incremental force delta F. At tatawagin natin tong frictional force F sub F. So, itong F sub F na to ay galing sa shearing stress tau na nasa curved surface ng ating cylinder or pipe. Now, we have F sub F tau times 2 pi y L. So, according to investigations, itong shearing stress na ito ay given by this relation. Mu times negative dV over dy. Ang negative sign sa equation na ito ay nag-indicate na yung V ay nag-decrease as y increases. Okay. So, nakuha na natin yung forces. Makukuha na natin yung frictional force F sub F. Okay. Now, nakuha na natin yung force na nag-act sa loob ng ating pipe. And we know that the pipe is under equilibrium. So, here are the forces na nakuha natin kanina sa pipe. And the forces are under equilibrium. Ibig sabihin, i-equate lang natin itong dalawang equations na to. Incremental force and frictional force. Yan. May equate silang dalawa. So, mula dito sa equation na to, madiderive na natin agad ang dV, V, and C through integrations and setting boundary conditions. Pag nakuha na natin yung dV from this equation, yan, makuha natin, magta-transpose lang tayo. Makuha natin si dV, i-integrate natin siya between 0 and y. So, ito yung ating dV na makukuha mula dito. Integrate lang natin siya between 0 and y and makukuha na natin yung V. Okay? So after nun, magsiset tayo ng boundary condition sa wall ng ating pipe where V is equal to 0. So papalitan natin ito ng 0 and y is equal to d over 2 or yung ating radius d over 2. So makukuha na natin si C. Okay? So substituting this value of C sa ating previous equation, makukuha na natin ang bagong equation na ito. Okay. So nakuha na natin ang bagong equation na ito. So this equation gives the velocity at any distance y from the center of a pipe na may diameter na d and length na L. Yung W dyan ay ang ating specific gravity. And yung yun naman natin ay ating viscosity ng flowing fluid. So ang graph nitong equation na to ay ito. Makikita natin na isa siyang parabola na merong axis through the center line noong ating pipe. Ibig sabihin, dun yung pinakamalakas yung velocity. Next. So, balik tayo sa ating unang figure. Kukuha tayo ng elemental ring na may thickness ulit na dy and radius na y. So, since meron tayong flow rate, alam natin na meron tayong flow rate sa loob ng ating pipe, itong elemental ring na ito ay may elemental flow rate na tatawagin natin dq. And this can be written as dq is equal to v times 2 pi y dy. So, substitute natin to sa ating nakuhang v kanina and makukuha natin tong equation na ito which can also be written as this equation. So, pag in-integrate natin tong equation na to ulit from 0 to d over 2, makukuha natin ang ating Hagen-Poiseuille equation which is written as Q is equal to pi W HF all over 128 mu L times d to the fourth. So, mula dito sa equation ng ating Hagen-Poiseuille equation na based sa flow rate, makukuha rin natin ang ating frictional loss HF under laminar flow conditions. So, pwede nating i-simplify itong equation na ito by further substituting itong value ng Q, which is alam naman natin na area times velocity. So, sa pipe na ito, makikita natin na ang area times velocity ay pi d squared all over 4 times V. Substitute natin ito at makukuha natin ang ating frictional loss HF under laminar flow condition. So, parehas itong ituturing na Hagen-Poiseuille equation dahil derived na sila sa isa't isa. Okay. So, makikita natin sa Hagen-Poiseuille equation na ito na ang flow rate sa loob ng isang pipe or cylinder ay nakadepende mostly sa diameter nito, sa laki, at sa length ng pipe, pati na rin sa viscosity or sa flow ng ating flowing fluid. So makikita natin na pag in-increase natin ang viscosity or ang mu at ang ating length or ang L, magdi-decrease ang ating flow rates. Since sila ay inversely proportional from each other. And pag in-increase naman natin si diameter, mag-i-increase din si flow rate since sila ay directly proportional. Okay. To understand the concept of this equation better, ito po ay ang may present po ako sa inyong video. Ay, pwede siguro yan. So, makikita natin sa video na mas marami yung outlet sa ating kaliwang tank kaysa sa kanan na tank. To be specific, 16 yung nasa kaliwa at iisa lang yung nasa kanan. Ngayon, ang pinagkaiba nilang dalawa ay ang kanilang diameter. So, makikita natin na although mas maraming outlet tubes yung nasa isang tank at iisa lang yun nandun sa isa, halos sabay pa rin yung pagbaba ng tubig, obviously, dahil mas malaki yung diameter nung nasa right tank. So, binuprove nito yung ating Hagen-Poiseuille equation na kapag ang diameter ng tube ay directly proportional sa ating flow rate. So, since in-increase yung diameter sa ating right tube or right tank, mas mataas din yung flow rate niya. So, here are some remarks. So, yan. First, there is no velocity at the solid boundary and that in laminar flow, shear stress is given by relationships tau yan, is equal to mu dv over dy. So, hindi lang ito assumed, kundi verified ito experimentally, hindi lamang ni Hagen at ni Poiseuille, kundi pati rin ng ating iba pang later investigators. So, next, Hagen-Poiseuille equation can be reduced into a form similar to Darcy-Weisbach equation. And ang equation na tinutukoy doon ay ito. HF is equal to 64 over Reynolds number times L over D times D squared over 2G. So which shows that the pipe friction coefficient F for laminar flow is F is equal to 64 over RE. So ito yung nasa kanina nating, unang-una nating page ng ating coefficient of pipe friction for laminar flow. Nagaling dito sa equation na ito. And lastly, last remark for this topic, the relationship of maximum velocity Vmax and the mean velocity V can be obtained through noting that Vmax occurs at y is equal to 0. So y is equal to 0 kasi alam natin na yung pipe natin ay ganyan, at yung y niya ay yung radius. So, pag sinabi mong y is equal to 0, nasa gitna yun. Okay? So, Vmax is equal to 2V. Itong relationship nito. Okay? So, now let's go to coefficient of pipe friction of the Darcy-Weisbach equation. So in this part, I will talk about the determination of F of the Darcy-Weisbach equation for pipes having different degrees of roughness and through which any kind of fluid flows. Hindi lamang water, kundi kahit anong kind of fluid. So, para sa pipes under laminar flow, kung saan ang ating Reynolds number R sub E is less than or about 2,000, yung head loss natin ay independent or hindi nakadepende mula sa degree ng roughness ng inner surface ng ating pipe. So kanina, na-determine natin sa Hagen-Poiseuille equation na yung value of F or coefficient of pipe friction sa under this condition or laminar flow ay F is equal to 64 over R sub E. Pero kapag ang Reynolds equation natin ay lumagpas ng 2,000 and umabot sa more than 3,000, in almost all circumstances, ito ay wala na tayo sa laminar flow, kundi nandun na tayo sa turbulent flow. Sa case na ito, ang coefficient of pipe friction natin, pati ang frictional loss or H sub F tsaka F natin ay dependent hindi lamang sa Reynolds number, kundi pati na rin sa relative roughness ng ating pipe. So, ang relative roughness is given by the equation epsilon over diameter or ang epsilon na to ay ang tinatawag or ang tinutukoy nito ay ang height of ating protuberances. So, ito yun. Yan. This is the epsilon. So, ito yung roughness ng ating pipe. Tapos, yung height ng bawat protuberances ay tinatawag nating epsilon. So, next. Sa table na ito, naka-indicate yung common values ng epsilon. So, iba dyan yan. Cast iron, 0.260 in mm to. Okay? So, for this condition, yung turbulent coefficient ng pipe friction ay makukuha natin sa formulas na ito. May dalawa tayong conditions under turbulent flow at ito ay ang hydraulically smooth and fully developed na turbulence. So, ang equations na ito ay itong dalawa. Okay? Later on, i-discuss natin itong hydraulically smooth at fully developed. Ano nga ba yung meaning nila? Pero so far, ito yung formulas nila. So, more conveniently, we can also use this table which I named figure 7.8.1. So, here are some remarks for this. Paano nga ba natin malalaman kung hydraulically smooth or fully developed? So, sabi rito, in turbulent flow, there is a layer known as boundary layer. Isang thin layer na adjacent sa ating pipe wall kung saan ang flow is still laminar. So it says here na if epsilon is less than the thickness of this layer, the pipe is considered to be flowing hydraulically smooth. So ibig sabihin, yung value of F is independent pa of the pipe's roughness. Pero if epsilon is greater than the boundary layer, then the pipe's roughness becomes a factor on flow turbulence and have a direct effect on the value of F. When the amount of turbulence has increased to a maximum value as a result of increase in Reynolds number, the flow turbulence is said to be fully developed. So ito namang condition na to, cause ito ng decrease ng thickness ng ating boundary layer. So, next, between these two conditions, hydraulically smooth and fully developed, meron tayong region given by this relation, 1 over square root of F, na suggested by Colebrook and White, 1939. And lastly, in the region where Reynolds number is greater than or equal to 2,000, but less than or equal to 3,000, in which the laminar flow is either laminar or turbulent, values of F corresponding to a Reynolds number of 3,000 is recommended para sa safety and design purposes. I hope you understood. Punta tayo ngayon sa ating sample problems. Sample problem number 7. An oil with density 900 kilograms over cubic meter and kinematic viscosity 0.0002 square meter over second flows upward through an inclined pipe as shown. So assume natin na this pipe is under steady laminar flow and i-compute natin itong following. Head loss between section 1 and 2, pati na rin ang ating flow rate. So ito yung ating figure. Yan. Papakita naman natin siya sa next slide. Solution. So una natin hinahanap ay head loss between section 1 and 2. So this is the section 1 and this is the section 2. So una natin gagawin, hahanapin natin si total energy head at point 1. And given yon by this equation. Pressure head is equal to pressure over specific gravity. And alam naman natin na ang specific gravity is equal to rho times gravity. Yan. So, substitute lang natin ng values mula sa ating figure. Ang pressure sa point 1 ay 350,000 Pascal all over ang rho natin na given kanina sa problem, which is 900 times gravity na 9.81. Mula dito, makukuha na natin si total energy head at point 1, which is 39.642 meters. Okay? So, hindi pa yun yung final answer since ang kailangan natin ay head loss between section 1 and 2. So, next, ang kailangan natin ay total energy head at point 2, given by this equation. So, since ito ay meron ng height, kailangan natin ng z. P over W plus z. So, substitute lang ulit. Ang P2 natin ay 250,000 all over specific gravity natin or rho times g, which is 900 times 9.81, plus yung z niya na 10 sine of 40 degrees. Okay? So, makukuha natin si 34.744 meters. Okay? So, makukuha natin si head loss by just subtracting these two. Total energy head at point 1 minus total energy head at point 2, and makukuha natin na 4.898 meters. Ganun lang kadali. Next na hinahanap natin ay si flow rate. Dito sa figure na ito. Paano natin mahanap si flow rate? Okay. So, alam naman natin mula sa ating derivation kanina na ang head loss ay equal to 128 Q mu L all over pi WD to the fourth, where again, W is equal to rho times G, and mu is equal to rho times ang ating kinematic viscosity na given kanina sa ating problem. So, pag sinubstitute natin ito, makukuha natin ang panibagong equation, and substitute lang natin lahat ng given natin, pati na rin mula sa problem, pati na rin sa figure, and ito yung makukuha nating equation. From this, pag sinolve natin ito, makukuha natin ang answer na Q is equal to 0.007642 cubic meter per second. So, madali lang. Okay? Next problem tayo, which is yung last problem natin for this section. Yan. Sign ko muna. A hypodermic needle has an inside diameter of 0.3 millimeters and 60 millimeters in length as shown. Yan. Ito po yung ating figure. The piston moves to the right at a speed of 18 millimeters per second, and there is no leakage. The medicine in the hypodermic has a viscosity of mu is equal to 0.980 times 10 raised to negative 3 Pascal per second. Pascal second. And its density is 800 kilogram per cubic meter. Consider flows in both needle and cylinder. Neglect exit losses from the needle as well as losses at the juncture of the needle and cylinder. Okay? So, mula dyan sa problem na yan, ito yung mga required natin. Kailangan natin ng pressure inside the needle, pressure inside the cylinder, and pati na rin yung force F needed dito sa piston na ito. Okay? So, proceed tayo. First ay pressure inside the cylinder. Okay. Makukuha natin yan through knowing that Q is equal to area times velocity. So from this figure, ang area natin, pi over 4 times 0.005 squared times 0.018. Mula yan dito sa ating cylinder. Kasi cylinder pa rin hinahanap natin. Palang hinahanap natin. Okay? So ang flow rate sa ating cylinder ay 3.534 times 10 raised to negative 7 cubic meter per second. Next, ito ulit ang ating equation. Mula sa ating equation, makukuha natin yung equation ng pressure, which is yung hinahanap, which is ang rho G times H sub F. So, ito po yun. Ito po yung equation na ito. 128 Q mu L all over pi T to the fourth. Yan po ang ating equation ng pressure. Mula dyan, Substitute lang po natin ang ating values. 128, yung nakuha po natin Q kanina. And then, ang ating mu na given sa ating problem, ang ating length na 0.05 meters, naka-meters po yan, kaya po lumiit. And then, ang ating pi d to the 4. Okay? So, mula dyan makukuha natin ang pressure inside the cylinder, which is 1.129 Pascal. Next po, pressure inside the needle naman tayo. So, dito naman tayo punta. Alam na natin na ang equation for pressure ay this one. Substitute lang po tayo. 128 times yung flow rate na nakuha natin kanina, times mu, na sabi sa problem, times length ng needle na 0.06 meters. All over pi times ang ating diameter, the 4. Makuha natin ang pressure inside the needle, which is 104,525 Pascal. So, mas malaki yung pressure niya since mas maliit yung diameter niya. Okay. Next tayo, last na po, force F needed on the piston. So, alam ulit natin, kanina recall natin, nasabi ko na force is equal to pressure times area. So, makukuha natin mula doon ang equation na to. Force is equal to P2 minus P1 times area. So, yan po. Makukuha natin ang force F through subtracting yung nakuha nating P2 or yung pressure inside the needle minus yung pressure P1 or yung pressure inside the cylinder times yung area natin, which is yung pi over 4 times diameter squared. Okay? Makukuha natin ang force F needed on the piston, which is 2.05 newtons. Yun lang po. Maraming salamat.
Good day, I'm Mark Suryo and I'm going to discuss about wetted perimeter and hydraulic radius that falls on open channel flows and hydraulic grade lines and energy grade lines which falls on pipe flows. Before I proceed, let me share my screen first. So, wetted perimeter and hydraulic radius. So, gaya nga ng sabi ko kanina, ang open channel flow ay doon nakabilang yung wetted perimeter, flow of area, and hydraulic radius. So, paapyawan muna natin yung open channel flow. Ang open channel flow ay branch na ng hydraulics, which deals on liquid flow within a conduit or in a channel with a free surface. From the word itself, open, yun nga, may free surface. Unlike pag pipe flow, di ba na ano natin yung pipe? Pag pipe flow, closed yung surface nun. Meaning, ibang-iba siya sa open channel flow kasi walang free surface na nagdetouch ng atmosphere dun sa pipe flow. So, yon ang open channel flow ay dependent sa sectional properties. When we say sectional properties, nagre-rely siya sa geometric aspect nung area mismo na kinabibilangan ng fluid na ine-investigate natin. Tapos yung three components niya is yung flow of area, wetted perimeter, and hydraulic radius. So yun, ang flow of area which is denoted by uppercase A is just the area of the section being considered. So example natin dito sa rectangle na to. Yung flow of area daw is yung na-occupy na area ng liquid dun sa section na yun. So para makuha natin yun sa rectangular section, multiply lang natin yung base tsaka yung height ng liquid na na-occupy dun sa section. Pag sa triangle naman, z times y squared. Tapos pag sa trapezoid naman, quantity b plus z times y times y. Tapos next tayo sa wetted perimeter, denoted by uppercase P. It's the line of intersection of the wetted surface with respect to the cross-sectional plane. So, ang wetted perimeter daw, yung line of intersection with respect to the cross-sectional plane. So, yun nga yung perimeter. Aware naman tayo sa word na perimeter. So, ito yung mga formula para mahanap yung perimeter based sa kung ano yung geometric aspect na meron yung section na ini-investigate natin. Tapos, yung ratio ng flow of area sa wetted perimeter, yun naman yung tinatawag natin na hydraulic radius, which is denoted by capital R. So, disclaimer lang, ang geometric radius is different from hydraulic radius. So, para mas maintindihan natin, mag-come up tayo sa isang example. Sample natin, problem 9. Referring to the trapezoidal channel cross-section whose normal depth is 3 feet, compute for the A, cross-sectional area of flow, B, wetted perimeter, and C, hydraulic radius. So, ang given natin is a trapezoidal channel na may depth daw na 3 feet. Tapos compute daw yung area of flow, wetted perimeter, and hydraulic radius. So, given din yung length ng base, pati yung letter Z. So, para makuha natin balikan natin yung kanina na formula sa trapezoid, which is, para daw mahanap natin yung area A, i-multiply natin yung quantity ng base plus yung Z times yung depth, as yung product nila ay yung sum ng product ng dalawa is i-multiply sa Y. So, yun. A is equals to Y plus quantity B plus Z times Y. So, i-plug in natin yung mga values kanina sa given na channel. Ang sagot natin is 28.5 feet squared. Then, after natin makuha yung flow of area ng cross-section, proceed na tayo sa wetted perimeter kasi di ba, recall natin, ang hydraulic radius daw ay ratio ng A sa P. So, para mahanap natin yung wetted perimeter, plug in lang natin yung values. Then, lalabas na yung size, yung length ng perimeter natin is 15.82 feet. So, para malaman natin yung hydraulic radius ng problem, i-ratio lang natin yung nakuha nating area dun sa na-compute nating wetted perimeter, which is 28.5 feet squared or square feet divided by 15.82 feet. So, ang hydraulic radius natin for that problem is 1.8 feet. So, proceed na tayo sa hydraulic and energy gradients in a straight pipe. So recall natin yung Bernoulli's equation, which is velocity 1 squared over 2g plus rho over lambda plus c is equals yun nga yung Bernoulli's constant. So sabi dito, HGL and EGL, yun nga yung hydraulic grade line and energy grade lines, are graphical representations of Bernoulli's equation. So ipapakita natin paano nga ba nasabi na graphical representation sila ng Bernoulli's equation. Isa-isahin muna natin. Hydraulic grade line, sometimes called piezometric headline, is represented by the equation rho over lambda plus z, where rho over lambda is pressure head and z is the elevation head. HGL is a plot of height. Tapos ang energy grade line naman is Bernoulli constant. Paano natin nasabing Bernoulli constant? Kasi yung buong equation ng Bernoulli constant, yun yung kailangan gamitin para mahanap natin yung energy grade line. Kasi since nga siya yung parang inaanong total na energy doon, magagamit natin siya sa real flows with viscous losses. So i-consider natin tong inclined pipe na pinakita para i-explain yung kanina. So sabi yung HGL daw, yung pinagsamang, yung sum ng pressure head and elevation head. So, yung elevation head natin dito is from a relative point from the arbitrary datum, which is yung sa baba, papunta doon sa pipe. Yun yung elevation head natin. Tapos yung pressure head naman natin is from the pipe hanggang doon sa na-reach nung piezometer natin. Kaya nga tinatawag yung hydraulic grade line na piezometer grade line din. Kasi nga, reliant tayo sa value ng sa piezometer. Tapos neglected natin yung taas kasi yun yung parang energy losses. Kasi nga ang energy grade line natin is yung pinaka-total. Kumbaga yung pag pinag-plus lahat ng energy na nasa system natin, ang lalabas na sagot ay yung energy grade line. Kaya tayo ng section 1 and section 2 para malaman natin kung ano ba yung progress ng hydraulic grade line, kung nagpro-progress pa or nagre-regress. So yun, mas nakikita natin yung gantong observation sa in viscid flows kasi nga constant lang yung energy content unless may kita natin dun, ma-observe natin sa hydraulic grade line kung nadadagdagan ba or nababawasan yung energy. Kasi di ba, nako-convert yung kinetic into pressure pag dinagdagan ng pressure into potential. So, for further explanation regarding how hydraulic grade line works as well as the hydraulic energy grade line, refer to this link below. Thank you. Okay, let's move forward naman sa minor losses. Earlier, nabigyan na ng brief background yung about sa head losses, yung sa pressure head nga. Bale, this time, explore naman natin yung conditions kung saan naman nagaganap yung concept of minor losses. Bale, i-introduce natin ay two subtypes, which is yung una is sudden contraction of pipes. Then yung pangalaw is sudden enlargement or expansion of pipes. Minor losses. So ano nga ba yung pagkakaano natin sa minor losses? Ang minor losses ay nagaganap sa isang piping system. Bale, yung flow ng piping system, di ba required siya na mag-pass through ng variety of fittings tsaka abrupt changes sa area na yun. So dahil doon, may encounter natin primarily, doon pa lang yung additional head losses, which is yun nga, na result nun ay flow separation, which is categorized under minor losses. So ang minor losses ay ma-express natin sa equation na minor loss is equals to K, which is yung coefficient na makikita natin sa table of values under kung anong category ba siya or condition nangyari. Then yung V is the velocity. Then yung G, yun nga, constant yan. Tapos, results from changes of velocity. Yun nga, velocity head yung pinag-uusapan natin sa part. So, eto naman yung una, sudden contraction. So, mapapansin natin, from a larger pipe into a smaller pipe. Sudden contraction. The loss of head due to sudden contraction may be expressed as head loss of contraction is equals to coefficient of contraction times velocity squared all over 2g, where velocity is the mean velocity in the smaller pipe. And yun nga yung coefficient na sinasabi ko, may express siya sa ratio ng D2 over D1, yung diameter ng second pipe sa first pipe. So paano nga ba natin ma-explain ng maayos tong sudden contraction? So isipin na lang natin na kunyari, yung entrance is from a finite reservoir. Doon pa lang malalaman natin na sudden contraction na between two sizes of pipes yung mangyayari. Bale, tingnan natin kung. Ito yung sinasabi ko earlier na table na pagbabasihan natin ng values nung Kc, which is yung coefficient nga ng sudden contraction. So, dyan natin makita yung about sa velocity, then yung sa ratio of first diameter ng pipe sa second diameter ng pipe. So, mas maintindihan natin siya with a problem. So, sample problem 13, what is the loss of head due to sudden contraction in a pipe carrying 57 liters of water, which suddenly changes from a diameter of 20 centimeters to 15 centimeters. Also find the pressure difference resulting from this change of section. So yun nga, based kanina, kailangan natin kunin yung ratio ng second diameter of pipe sa first diameter of pipe, which is nabanggit na sa problem. And ang nakuha nating ratio is 0.75. Then dahil nakuha na natin yung ratio, kukunin naman natin yung velocity ng bawat pipe. So yung radial velocity yan. So yung sa taas yung mass na given na 57 liters of water. Then sa baba naman yung size ng pipe, which is yung 20 centimeter pero kailangan natin gawing meter. So 0.20. Then mapapansin natin yung final velocity is mas malaki compared sa nauna. Then based sa formula, ang kailangan daw gamitin nating velocity is yung final velocity, which is yung sa smaller pipe. So ang nakuha nating velocity is 3.2. So magbe-base na tayo dun sa table of values kanina na pinakita ko. So mapapansin natin wala namang 3.2. So ang gagawin natin, magli-linear interpolation tayo. So kunin natin yung kung ano yung values ng set 3 to 6, then hanap tayo ng way doon para malaman natin yung values ng 3.2. So yun nga yung nangyari dito. Let V2 is equals to 3.2 meter per second. Then yun nga, yung nasabi kong linear interpolation ginawa. Ang nakuha nating value ng coefficient of sudden contraction ay 0.14. So i-plug in na natin siya sa formula, which is yung head loss equals to Kc final velocity over 2g. So yun nga, 0.14 times 3.20 squared all over 2 times 9.81. Ang sagot is 0.073 meters. So naano na natin yung loss of head na hinahanap sa problem. Then proceed tayo sa next natin hinahanap sa problem. Find the pressure difference resulting from this change of section. So yun, gagamitin ulit natin yung Bernoulli concept na ni-recall natin kanina, which is ito yung sa first pipe, then ito yung sa second pipe kasi nga doon nangyayari yung head loss. Then yun nga, plug in lang natin yung values. Ang nakuha natin ay 4.32 kilopascals. Then proceed naman tayo sa sudden enlargement. Ano mapapansin nyo sa sudden enlargement? So unlike earlier na from a bigger pipe to smaller pipe, ito naman from a smaller pipe into a bigger pipe. Then the loss of head due to sudden expansion or enlargement is similarly expressed as a fraction of the velocity head in the smaller pipe. So hawig din nung formula earlier yung formula sa sudden enlargement. Pero kasi yung dito naman sa sudden enlargement, nauna yung smaller pipe kaysa sa bigger pipe. So ang kukunin nating velocity is yung initial velocity kasi nga nauna yung smaller pipe. Tapos yung KE nga, yung dimensionless coefficient naman na nakabase sa table of values dun sa sudden enlargement. Then reliant pa rin yung values na nandun sa ratio between the first diameter and the second diameter. So ito nga yun. Ito yung table 7.13.2 yung sa sudden enlargement. Tapos yung table 7.13.3, ito naman yung sa gradual enlargement. Parang special case siya ng sudden enlargement. So, pakita natin sa problem. Problem 14, what is the loss of head due to sudden enlargement in a pipe carrying 57 liters of water, which suddenly changes from a diameter of 15 centimeters to 20 centimeters. Also, find the pressure difference between 2 points before and after the change of section. So, yun nga. Unang process natin is hanapin yung ratio between the first diameter and the second diameter. So 0.75. Then kailangan natin i-obtain yung radial velocities from the two pipes, which is the first pipe has 3.20 meter per second while the second one has 1.8 lang. So mapapansin natin mas mataas yung radial velocity ng first pipe. So yun daw yung gagamitin natin na value para mahanap natin yung coefficient of sudden enlargement. So wala ulit 3.2 dito, so magle-linear interpolation tayo like before. Then ang lalabas na sagot is 0.195. Then yan yung ipa-plug in nating value sa formula ng head loss due to sudden enlargement. Then yun, plug in lang 0.195 times 3.20 squared all over 2 times 9.81, which is yung constant ng gravity. Ang sagot natin ng head loss is 0.10 meters. Then hanapin din natin yung pressure difference. Then katulad nung kanina, ang makuha nating sagot ay 2.55 kilopascals.
Good day, I am Janet Olfashol and I will be discussing about branching pipes, 3 reservoir problems. There are 2 cases that we must consider in analyzing 3 reservoir problems. To start off, let us look at this diagram. Consider reservoir A, B, and C connected to a common junction J through pipes 1, 2, and 3 with friction losses HF1, HF2, and HF3 respectively. Assuming that the pipes are sufficiently long, meaning their lengths are greater than 1,000 meters, we can say that in this case, minor losses can be taken negligible. By reason of continuity, what flows in and what flows out of junction J are equal. And with this, we can derive a continuity equation that is Q1 plus Q2 is equal to Q3. Under this flow condition, the liquid surface on the piezometer will be below reservoir A and reservoir B. With head losses specified, we can derive certain relationships within our components, one of which is HF1 minus HF2 is equal to the elevation of reservoir A and B, or H1. Another is HF1 plus HF3 is equal to the elevation of reservoir A and C, or H2. If H1 and H2 are known, these equations can be solved using trial solutions or trial and error. However, in cases where the pipe element F or N are given for each pipe, together with length L and diameter D, these equations can be solved simultaneously. That is for case 1. For case 2, where the flow in second pipe is towards reservoir B, the liquid surface on the piezometer rises to a point above that of reservoir B but below reservoir A. Under this flow condition, the continuity equation now becomes Q1 is equal to Q2 plus Q3. Other head losses relationships are HF1 plus HF2 is equal to H1, and HF1 plus HF3 is equal to H2. Notice that this last equation, HF1 plus HF3 is equal to H2, is similar with our first case. That is because the flow in second pipe does not affect the flow in the first pipe and third pipe. The three reservoir problem is the particular case in which the direction of the flow in pipe 2 is usually unspecified. This particular case is solved by considering the following assumptions. First is we assume that pipe 2 is closed. Therefore, HF2 is equal to 0. This condition makes HF1 equal to H1 and HF3 equal to H2, which in actuality is not true. Under this consideration, Q1 and Q2 may be obtained from either the Darcy-Weisbach or Manning equation by assuming trial values of F or N if these values are not given. If our Q1 is greater than Q3, the flow in pipe 2 is directed towards reservoir B. If Q1 is less than Q3, the flow in pipe 2 is directed away from reservoir B. Finally, the continuity equation and the head loss relations are written based on the result obtained from A and B. The system of equation thus formed is solved in the manner of foregoing method. To understand these concepts better, let us try solving this problem. Determine the flow into and out of each reservoir in the pipe system shown. The properties of pipes are L1 is equal to 1,200 meters D1 is 30 centimeters, L2 is 900 meters, D2 is 20 centimeters, and L3 is equal to 1,500 meters, D3 is equal to 15 centimeters. In our problem, the flow direction in pipe 2 is not initially known. So we assume that this pipe is closed. Therefore, HF2 is equal to 0. HF1 then becomes H1 and HF3 becomes H2. To solve for HF1, we subtract the elevations of reservoir A and B. That is 30 minus 24 is equal to 6 meters. To solve for HF3 or H2, we subtract the elevations of reservoir A and C. That is 30 minus 15 meters is equal to 15 meters. Since the value of our pipe element N is given, we can use the Manning equation. That is HF is equal to 10.3 N squared times LQ squared is equal to D raised to 16 over 3. Since we have the values of HF1 and HF3, we can solve for Q1 and Q3 using our Manning equation. Solving for this, we get the value of Q1, that is 0.081 meter cube per second or 81 liters per second. And Q3 is equal to 0.018 cubic meter per second or 18 liters per second. Since our Q1 is greater than Q3, the flow is towards reservoir B, and from this resulting direction in the system, we can use the following relationships. So we will analyze this problem using case 2. And from case 2, we get this following equations. Using the Manning equation for A and B and substituting all known information on the pipes, we can get the equation for Q2 and Q3 in terms of Q1. Then we will solve this equation. We will substitute this equation into our continuity flow direction. And we will get this equation. And from this, we can get the value of Q1, that is 0.043 cubic meter per second. We will then substitute this value of Q1 to the equation for our Q2 and Q3. And then we will get the values that are Q2 is equal to 0.027 cubic meter per second and Q3 is equal to 0.016 cubic meter per second. Another problem, 3 reservoirs A, B, and C are connected respectively with pipes 1, 2, and 3 joining at a common junction P. Reservoir A is at elevation 80 meters, Reservoir B at elevation 70 meters, and Reservoir C is at elevation 60 meters. The properties of each pipe are as follows. The flow from Reservoir A to junction B is 0.045 cubic meter per second, and F for all pipes is 0.018. In this problem, we are required to find the elevation of the energy grade line at P in meters, the flow on pipe 2 or Q2 in cubic meter per second, and lastly, the diameter of pipe 3 in millimeters. First, we need to find the energy grade line at junction P, which we represented as P prime. And in order to solve for this, we need to subtract the elevation of A by HF1. To solve for HF1, we can use the Darcy-Weisbach equation since we are given the pipe element F. So HF is equal to 0.026 FLQ squared all over T raised to 5. From this, we can get the HF1, which is equal 6.195 meters. The elevation of P prime is equal to elevation of A minus HF1 or 80 minus 6.195 meters, which is equal to 73.805 meters. Since the elevation of P prime is higher than the elevation of reservoir B, we can say that the flow direction in the second pipe, Q2, is towards reservoir B. This flow condition again falls under case 2. So next we will solve for Q2, but first we need to solve for HF2. In order to solve for HF2, we will subtract the elevations of P prime and B. That is 73.805 minus 70. HF2 then is equal to 3.805 meters. Since we have HF2, we are given with the values of F, L2, and D2, we can solve for Q2. Q2 then is equal to 0.025 cubic meter per second. And lastly, we will solve for the diameter of pipe 3. At junction P, the equation of continuity is Q1 is equal to Q2 plus Q3. Since we have a given value for Q1 that is 0.045 and we already solved for Q2, we can solve for the value of Q3. That is 0.02 cubic meter per second. HF3 can be solved by subtracting the elevations of P prime and C, 73.805 minus 60. HF3 is 13.805 meters. Since you have now the values of HF3, Q3, and L3, we can solve for the value of the diameter using again Darcy-Weisbach equation. So solving for this, we now get D3 is equal to 0.172 meters or 172 millimeters. Try solving this problem using the concepts we learned in this discussion. That would be all for branching pipe, 3 reservoir problems. Thank you for listening.